We'll see if anybody is here. Give it 5 minutes for people to show up. Go lessons. Week 2. Underpinning algorithms. Okay. Let's also make sure we have a link to that in the file. So we go here. Week 2, we go where is the main README is right there. Go week 1, week 2, copy, paste, week 2. Rhythms and data structures, and this is a lessons week 2.md, and let's commit that to the repo, and we will check to see if anybody is here in just a moment. 7 o'clock. There's probably a few minutes for people to show up. Otherwise, I guess I'm probably presenting to myself. Let me see. Actually, maybe I should check to see if I'm... Oh, hey, Rajat! Happy to see you here. I was worried that I'd be presenting to myself this week. We'll see if Josh and Glenn show up. And Love Pebs. See who else arrives. Source. So what is this? This is added link to week 2 lesson plan. Might just be you and me though, which is okay, because if it is just you and me, they can come back and watch via YouTube or something, because they are all linked up on YouTube, and so there is no there's no problem in missing a lesson. It just makes it harder for me to present, because any questions I get are useful for fleshing out the things that I might be missing in terms of what I am delivering. So I'm going to load up Twitch to see if anybody else is in the channel, and otherwise we can just get started. It doesn't have to be a super long week either if we move the mic there. And so this tells me who's here, and it is not telling me anybody. Okay, well, whatever. So mod view. Okay, next. Okay, skip all of this. I maybe watch that later. Okay, this is interesting. Okay, so I can see you are here. I can see... Actually, that's weird. I don't actually see anybody else. List is up to date. You'll have to wait a few seconds. So you are here in chat. Rajat, are you watching on YouTube or are you watching on Twitch? Because... Oh, Glenn! Hooray! Twitch. Okay. Well, it's weird because Oh, there we go. So now I see Pebs is here. Rajat. Glenn has just said hi. So we know that they have arrived. So, huge news to kick off this week's story. I actually got a job today. And so now step 2 is making sure that everybody else who wants to get a great new job has their has everything taken care of for them. But for me, I am done and dusted. I'm so excited about it. So at the end of the month, is when I start at the new place. I'm so excited. One of the things that is really exciting about the new role is they actually like that I'm doing this Twitch stuff and this podcasting thing and the YouTube show because they see it as an opportunity to to do tech marketing for recruitment for their shop. And so when I actually start, I'll be doing things like writing blog posts and maybe producing content for technical content for them. So sort of probably along the lines of this stuff, like helping people in the community and building a community so it raises the profile of their company's name with the Toronto and the wider tech community, and hopefully makes it easier for them in the long run to bring on new team members, right? So, because if you build a name for yourself as a technology hub, then I think it probably becomes a little easier to bring other people online. So it is just so exciting to have that, and that's about 20% of the time allocated to the role will be just doing that sort of community content thing. And so it's really cool that this is something that I would be doing anyways. But now one day a week at work is going to be doing this stuff. So like now let's take care of the rest of you and anybody else who is watching. So oh, I have another story that I wanted to tell right off the start before I get into this, and it is about the... No, I'll tell it later. We will talk, but there's I actually failed an interview last week as well, and it was an algorithms interview, and I think part of what I want to talk about in terms of learning these algorithms and doing this work is around making sure that we are completely aware of the scope and importance of these algorithms that we're studying. It is so suspenseful. But stay tuned. So this week we're going to start back at the roadmap. This is the structure that has been laid out for us by everyone else, or by someone else, and it's start reviewing the concepts like data structures and algorithms. Some of us did not do data structures and algorithms in undergrad, and so it is not in fact a refresher. I think Rajat's probably the only one with a CS degree, but for the rest of us, we want to learn what these things are for the first time. And now this part right here, it says they're actually quite useful in coding interviews, but I actually think that they're quite useful in coding full stop. And so I don't want to underplay the value of what we would be talking about in terms of doing this. Like these two things, I actually didn't go through these links, but they are certainly valuable links to go through. I went ahead, and so we've got two topics that I think are kind of the hardest to deal with are complexity analysis, and hash tables aren't the hardest, but one of the resources that I went in preparation for tonight's work said that, like, if I find the quote, let me go back to the spot where we have it. It's one of the, I think, Gail. Yeah, so Gail Lackman McDowell is the author of. Let me grab the books that I have here again. So we're going to pull up Gail Lackman McDowell. Oh, here we go. So she wrote Cracking the Coding Interview. And you can see her name there, Gail Lackman McDowell. So she had this insight in her, in one of the YouTubes that we're going to watch, where she says, a good rule for interview questions is it's always a hash table. The answer is always use a hash table, was what she wound up saying. And anyways, so we'll go back up. So the things that we want to come away with this week is an understanding of BigO notation. We want to have a list of places to find the resources to do the studying that we're going to do. We're not going to do all of the studying. I'm going to highlight BigO, and I'm going to highlight hash tables this week, but I'm not really going to go into, if we look at the rest of this, arrays I think are probably pretty easy. Stacks, queues, links, we're gonna maybe I didn't pick enough this week. Maybe I should have done 3 things this week instead of just the 2. So we'll find out. We'll find out if I haven't scheduled enough, if I am a terrible human being. So the first thing I want to watch together, and I'm not going to do it at 2 time. For Rajat, because I know Rajat was saying he has trouble listening to the things when I'm going at 2x speed, but like, we'll try 1.5. If it's too fast for you, let me know and we can slow it down. One of the tips that I learned from my sister-in-law, who is a medical doctor, she. Okay, 1.5 should be fine. Okay. Yeah, she says that, like, she studies all of her stuff at 2x speed, and you just have to sort of train yourself to get used to it, but 1.5 is fine as well. That's autoplay is off. What's my...
I mean, everyone assumes you're a genius. You get high-paying offers from prestigious companies, and you even have a high social market value on internet forums. But the journey from lead sell to algo chat is not an easy one. It's filled with frustration and imposter syndrome. I know I've been there, but now I have offers from FAANG, which basically qualifies me to cure cancer. So to give back and help even the most confused of programmers, consider this video my cure, since this industry is cancer.
He's young.
The most important part of learning something new is that you actually want to learn it. This is why I failed on Spanish 1. So before we start, ask yourself, why do you want to learn this? Don't do it to get a job at Google. Do it because learning this changes the way you think. Data structures and algorithms is about solving problems efficiently. A bad programmer solves a problem inefficiently, and a really bad programmer doesn't even know why their solution is inefficient. So let's start with that. How do we rank an algorithm's efficiency?
So you want to be a software engineer at Google? Go to
Worst.
algoxx.io. Pick a question. Read the prompt.
Say you are a function that goes through every number in a list and adds it to a total sum variable. If you consider adding to be one operation, then running this function on a list with 10 numbers costs 10 operations. Running it on a list with 20 numbers costs 20 operations. Say we wrote another function that just returns the first number in a list. Then no matter how large the list is, this function will never cost more than one operation. Clearly, these two algorithms have a different time complexity or relationship between...
So the little quiet. Let me try turning it up. Yeah. So the first thing that we're talking about here is... he's talking about BigO notation, time complexity, which we're going to go over this one 3 times for the maybe 2 times, at least 2 times. But this one's this one really matters. So that's why I wanted to do this one. But also this particular video is he covers like a high level overview of everything, and so it's, let me actually double check because my computer is at 100% as well. But so this video covers a high level breadth first sort of coverage of everything. You're not going to be an expert in anything by the end of it. You're just going to have a fundamental sense of what things are definitionally, but you're not going to, each one of the topics that we have to cover goes into more and more and more detail. But it's nice to sort of have this shallow exposure right off the bat so that when it comes up again, you have this more this mirror exposure effect in terms of understanding what you're about to talk about. So let him get back to it.
Growth of input size and growth of operations. We communicate these time complexities using BigO notation. Referring to input size as n, common complexities are constant, linear, quadratic, logarithmic, n log n, exponential, and factorial. Our first algorithm runs in O of n, meaning its operations grow in a linear relationship.
Let me back that up as well so that that's the... What have I done? Why am I the worst human ever? Okay. We were right here.
BigO notation. Referring to input size as n, common complexities are constant, linear, quadratic, logarithmic, n log n, exponential, and factorial.
Okay. So what he said so far about what BigO notation is, or time complexity notation is how long would you expect the function that you write to take based on a variable number of inputs. And so there are some operations that take the same amount of time no matter if you're doing 100,000 entries or if you're doing 1,000,000 entries. It's just do a snap and it's done. The log n version is something in business we refer to that kind of as the law of diminishing returns, where you do this much more work but you only get this much more benefit out of it. This is the inverse, where you can double the amount of records, so you're doing 1,000,000 records instead of 100,000 records, but it still only takes you a microsecond longer. And then each of these is sort of along that scale. So linear progression means for each additional element you have one additional time unit to deal with. And it isn't about the exact amount of time, it's about the rate of change in time.
Our first algorithm runs in O of n, meaning its operations grow in a linear relationship with the input size, which in this case is the amount of numbers in the list. Our second algorithm is not dependent on the input size at all, so it runs in constant time. Let's take a look at how many operations a program will have to execute in a function with an input size of 5 versus 50. It might not matter when the input is small, but this gap gets very dramatic as the input size increases. If n were 10,000, a function that runs in log of n would only take 14 operations, while a function that runs in n factorial would set your computer on fire. For BigO notation, we drop constants, so O of 10 times n and O of n over 10 are both equivalent to O of n because the graph is still linear. And BigO notation is also used for space complexity, which works the same way for how much space an algorithm uses as n grows. Unless you sit in your room doing algorithms all day, there's a good chance you forgot what logarithms are. Logarithms are the inverse to exponential functions. Let's say I wanted to find a word in a dictionary. One method is to check every word one by one. This is O of n. But nobody does that. So how are humans able to find any word in a dictionary with 100,000 words in seconds? We do something more along method 2. Cut the search window in half each time by checking the middle element. If we passed our word, search in the left half. Otherwise, search on the right half, and then we repeat this until we find our word. If our input n doubled in size, that would only grow our operations by 1. In computer science, this is the binary search. But for the binary search to work, the collection has to be sorted, which opens up a huge field of computer science. Sorting algorithms. A very basic sort is a selection sort. You have one pointer at the start of the list, and another pointer that is linear scan to find the next minimum element. Then you swap those elements and increment the pointer. Since you're doing a linear scan for every element in the collection, this results in O of n squared. A more efficient algorithm is a merge sort. A merge sort splits a collection in half into sub-collections until those sub-collections can be sorted in constant time. And then it works its way back up by merging sorted sub-collections until the entire collection is sorted. Since it's splitting in half, there will be log n splits, and thereby log n merges. It is O of n to merge 2 sorted collections into 1 sorted collection. Since we're doing that log n times, the time complexity is O of n times log n. No algorithm can sort an arbitrary collection in a better time complexity than that, so we consider n log n to be the cost of sorting. Perhaps the most fundamental data structure is an array. An array is an indexable, contiguous chunk of memory. Arrays are fixed size. You can't insert a 9th element into an array meant for 8 elements. A list data structure with a flexible size is a linked list. The idea is to package your data into nodes that hold 1, your data, and 2, a pointer that points to the next node. Traversing a linked list reminds me of those YouTube direction chains. Like you see a comment that says, read my profile picture, and the profile picture says, click on my profile, which brings you to their header which says, read my bio. So you go to their bio and it says, click the link below, and you click it, and then it installs a virus onto your browser. If a node's next pointer points to null, it's the end of the list. You can add a new node to the list in constant time by just setting that pointer to the new node. By doing additional tomfoolery with pointers, we can also insert and delete nodes in constant time. Sometimes nodes also contain a pointer to the previous node in a variation called the W linked list. But a major downside of linked lists is that you can't access elements in constant time via index like an array. In practice, most programming languages have dynamically sized arrays or lists, which work by creating arrays with a fixed size. If the array is full capacity and you try to add a new element, the programming language automatically creates a new array with double the capacity, copies the current elements over, and sets your pointer to that new array. Since this happens so infrequently, we generally consider appending to a list to be a constant time operation.
So you want to be a software engineer at Google? Go to algoexpert.io.
Pause for a bit and talk about, just sort of refresh the things that we've just seen. Maybe 1.5 if you're watching this for the first time is not ideal. Maybe I slow it down as well, but it's still gonna go fast. This one is linked right here. You can watch it again yourself 4 times, 5 times, just the spots that you've got there. So we talked about arrays. If you've used arrays, that's just a line of elements in a row, one after another. What was interesting about this version to me was he went further to talk about how they work at the memory allocation level. And he started talking about things like the time complexity of executing operations on these various data structures, all of which, for the high-end tech coding interview questions, for I assume the Googles and the Amazons, you would likely have a chance of being asked that. It's less likely at a mid-tier tech company. But in your day-to-day work, it's also really useful to have these things in the back of your head where you can understand where you can kind of understand what's actually happening at any given time. So we're talking about the linked list right now. It's a lot like an array, but it's not one. Anyways, and now trees.
Linked lists aren't the only data structure that include nodes referring to other nodes. What if instead of pointing to a next node, nodes pointing to a left and a right child node? This is called a binary tree. These child nodes can also be called subtrees since trees are recursive in nature. A node with no children is called a leaf node, while a node with 7 children is my mother-in-law. A common type of tree is the binary search tree, which follows these rules. Basically, a node's left child must have a smaller value, while a node's right child must have a greater or equal value. Let's say you're looking for element x. You start at the root, and if the number is smaller than the root, you go to the left tree. If it's larger, you go to the right. And you keep repeating this until you arrive at your number. In the worst case, you have to traverse the height of the tree. So the time complexity to search, insert, and delete elements is O of h, where h is the height. This is efficient because on average, the height will be log n. But what if you inserted every element of a sorted array into an empty binary search tree? Well, that's a linked list, meaning the height would be n. But we can guarantee log n time complexities using a self-balancing binary search tree, such as red-black trees, which maintain additional properties to guarantee that the height of the tree is O of log n. Binary search trees are kind of considered to be a workhorse data structure that can solve most problems with decent efficiency, but I found situations where binary search trees really shine are when you're asked a question about binary search trees. Another type of tree is a heap.
I mean, helpful to pause and think for a second at what we just saw, because there was the bit right here.
Binary search trees, red black trees, which
So
additional.
we've got our binary search tree or our binary tree where things are, you've got your node where at each point it either goes left or right based on the size, and so by default you have this sorted searchable item. And he's talking about another feature, another thing that might come up in terms of data structures. They might say, well, what is a red-black tree? And I see the word every once in a while happening in my research, and so it would appear from what Tren is saying that a red-black tree what would be the right word for that? Self mutates or self modifies to make sure that it constantly rebalances itself, versus a regular one, which he talked about a second ago. Anyways, so
the height of the tree is always log n. Binary search trees are kind of considered to be a workhorse data structure that can solve most problems with decent efficiency, but I found situations where binary search trees really shine are when you're asked a question about binary search trees. Another type of tree
Heaps.
is a heap. The primary difference between this and the binary search tree is actually use this one. It's also sometimes called a priority queue because at the root of it is always the highest priority element. A min heap will have the min element, and a max heap will have the max element at the root. But don't get me wrong, the rest of the heap is unsorted. It is an absolute wasteland down there. Searching in the rest of the heap may as well be an unsorted array. We only care about what's at the top. Just like capitalism. To insert a new element into a heap, first we find the next available spot to add a leaf node. Then we compare it with its parents, and if it's a higher priority, it swaps and bubbles its way up. We're doing at most log n comparisons. You can build a heap from a random collection by inserting n times, which costs O of n log n, but there's also a way to build a heap in O of n time. I'd suggest reading this Wikipedia page because it's super interesting stuff. And lastly, since the heap is nearly complete, although we can visualize it as a tree, we can actually use these properties to represent it with an array.
I didn't really get that one, so you might be on your own for that, or just, again, the point of going through this and going through this at high speed is not to know everything on the other side of it, but to have a better sense for the places where you are strong versus the places where you need to do more work. And so for myself, coming out of that, I would look at this and I would say, maybe I do a little more research around heaps. And then, anyways, so.
One way to traverse a tree is a depth first search, which is like going deep, fully exploring one path, and then moving on to the next. One way to visit this tree in a depth first order could be to start at 10, go to 13, go to 4, then 6, then 12, then 8, and then 1. Whereas another option is a breadth first search, where we view it more level by level. A way to print the same tree in a BFS manner could be 10, 13, 12, 4, 6, 8, 1. When it comes to implementation, depth first search can use a stack. A stack is a list-based data structure where the only two operations are add to the end and top from the end. This makes a stack lethal, last in, first out. DFS are often done using recursion, which indirectly uses a stack, the recursive stack. So if your recursion exceeds a certain amount of depth, then you get a stack overflow. Let's look at a way to print this tree in a DFS manner using a stack. So first initialize the stack and add the root. Then while there are still elements in the stack, pop from the stack, print that element, and then add its children to the stack. On the contrary, a breadth first search uses a queue. A queue is FIFO, first in, first out. So instead of popping from the end of the list, you pop from the beginning. Doing the same algorithm as before, but using a queue instead of a stack, the tree will now print in a BFS order. All trees are graphs, but not all graphs are trees. A graph is a...
So the two things that we had there were stacks and queues. A stack is quite literally a memory system where you put something on top of the stack, and if you want to get it off of the stack, you take it off of the top. Take it off of the top. And a queue is probably more like a line, where if you put something into the line, it comes out of the front of the line, right? So those are stacks and queues. And that unlike heaps, I have less trouble with that, and there you go. And there's a whole website named Stack Overflow, so now you know what that is for sure too.
collection of vertices, which are like points, and edges, which are like connections from one vertex to another vertex. A graph can be directed, meaning edges can only go one way, so this edge means you can only go from A to B, or undirected, meaning you can also go from B to A. Two common ways to model edges are adjacency lists and adjacency matrices. Graphs are my favorite part of data structure algorithms, so I like to show how cool they are with 3 example scenarios on where you can use them.
The rocket equation, it's a beautiful thing. No astronaut.
So it recently dawned on me that I know Kanye West. And by that, I mean I know Joe Matek. But Joe Matek knows Jarvis Johnson, who knows MKBHD, who knows Elon Musk, who knows Kanye West. Which is 5 degrees of separation between me and Kanye West. I wanted to find something shorter. Well, turns out I know Bretman Rock, who knows Rihanna, who knows Kanye. 3 degrees of separation. Which also means that anyone who knows me is at most 4 degrees of separation away from Kanye. If we wanted to make a program that computes the smallest degrees of separation between 2 people, a graph would be the perfect choice. You model people as vertices and you model relationships as edges. The shortest path between the source node, me, and the target node, Kanye, can be found with a breadth first search. Since we're moving out level by level, we can guarantee that the first time reaching the Kanye node will also be the shortest path. The problem with implementing this algorithm the way I just described is that nobody has a concrete list of all the people they know, nor would that be publicly accessible by me, but a possible variation could be in a social network like Facebook, where we can use the friend list as edges. We would then be able to run this algorithm and find the smallest degrees of separation between any 2 users in that social network. Imagine a map system like Google Maps that wants to find the shortest path between 2 locations. This is different from the last example because although they both deal with shortest paths, the degrees of separations did not have weighted edges where a map system does. For example, if we're computing the shortest path between 2 vertices and there's a direct edge between them weighing 20 versus a path of 2 edges weighing 8 each, a breadth first search would give us the shortest path in terms of vertices away, but not the smallest weight. One algorithm that computes the shortest path in a graph with positive weighted edges is Dijkstra's algorithm using the heap data structure. In the original version of this video, I explained Dijkstra's and the video.
What's interesting is I've started reading Clean Architecture, and I did not know this because Dijkstra's name comes up repeatedly, but he is credited with being the first ever programmer. Also, I do not expect that in a coding interview you will have to know anything about Dijkstra's algorithm, but there you go. Anyways, first ever programmer.
Shot up to 6 minutes, so instead just research it for yourself if you're interested. But graphs aren't just good for pathfinding. Imagine a course schedule in school with classes and prerequisites for each class, and say you want to find the order in which you can take all your classes while still fulfilling prerequisites. Well, model the classes as vertices and prerequisites as edges. Count how many incoming edges each vertex has. Add vertices with 0 incoming edges to a queue. Then pop and print the element from the queue and decrement the incoming edges of all its children. If a child now has 0 incoming edges, add it to the queue and repeat while there are still elements in the queue. This algorithm is known as a topological sort.
Right. So again, graphs are in the list, and so if you know, this again, top level overview. It's expected to feel like a fire hose, but when you come back to it, you will hopefully have a stronger understanding of what you're hoping to come away with. I hope this is not overwhelming or painful. Hashmap. Now, Hashmaps is one of the ones that is super duper important. So there you go.
Hashmaps are sort of the holy grail of data structures. With basically constant time retrieval of data, the saying goes that if you don't know what you're doing, just try throwing hashmaps at the question. As an example, one time I was in a coding interview and froze, so I just told the interviewer, I think the solution is to use a hashmap. Unfortunately, the question was, what are your biggest weaknesses? So the better answer was hang up the phone to show that I have none. A hashmap is a data structure built on top of an array optimized to store key value pairs. What makes it so powerful is you can retrieve, delete, and store data in, on average, constant time. Here we have a map where keys are strings representing people's names and values are their corresponding ages. We can directly access Tremblack's age like this. It's almost as if strings can be used as indices. But how is that even possible? Because of this little thing called a hash function. A hash function will take a key and return hash code. If we take that number modulus the length of its underlying array, we can use that as an index to store its value. But the hash function has to compute the same hash code if given the same key. So hash of Tremblack should always return the same hash code, or else we lose the index. But what if hash of Tremblack and hash of Ziz both end with the same index? Well, this is called collision. One way to deal with this is to store our value in a linked list. So when we go to store Ziz and see that index 3 already has a value, we have that value point to the new value. This is why a hashmap is not strictly O of 1, because if you write some god-awful hash function, then it won't be balanced, and we'll have to do a lot of linked list traversing. Good hash functions evenly spread out hash codes. In practice, modern languages use very good hash functions, so you don't have to write your own. An example of a hashmap is the dictionary in Python or the object in JavaScript. And remember, constant lookup of data is very overpowered, so try to use it when you
Remember to sign up for our completely free webinar for everyone who wants to start programming.
can. And that's pretty much all you need to know for data structures and algorithms. A 6-month college course taught in 13 minutes. Now, of course, you didn't learn anything in great detail, but trust me, it is a lot easier to learn something in great detail if you already learned the big picture first. This is why college sucks at teaching. It dives very deep into one topic and then moves
Okay, so we don't need to listen to his everything else. But the hash map is just an object in JavaScript. It's a key value pair. It's a very efficient data structure because it is said to be effectively constant time to get to your keys, and so and in terms of everything else, if you listen to Gail Lackman McDowell, she'll say everything's a hash table. So the next one that I think we should do, it's 7:30 now, is I don't know if we should do the full 30-minute or just do Gail's 8-minute. Let's go with the 8-minute one. And maybe we skip the 30-minute one. Here we go.
Hi, I'm Gail Lock-McDowell, author of Cracking Coding Interview. Today we're going to cover one of my favorite topics, which is BigO, or algorithmic efficiency.
Let's just do it at normal speed. This one's important.
Back in 2009, there was this company in South Africa, and they had really slow internet. They were really, really frustrated about it. And they actually had 2 offices about 50 miles away. So they set up this little test to see if it would be faster to transfer a big chunk of data over the internet with their really slow internet service provider, or be a carrier pigeon. Literally, they took a bunch of USB sticks, or probably actually one giant one, strapped it to a pigeon, and flew it from one office to the next. And they got a ton of press over this test, and media kind of loves this stuff, right? And of course the pigeon won, right? It wouldn't be a funny story otherwise. And so they got a whole bunch of press over it. And people were like, oh my god, I can't believe that a pigeon beat the internet. But the problem was, it was really actually kind of a ridiculous test. Because here's the thing. Transferring data over the internet takes longer and longer and longer with how much data there is. With certain simplifications and assumptions, it's not really the case with pigeons. Pigeons might be really slow or fast, but it always basically takes the same amount of time for a pigeon to transfer some chunk of data from one office to the next. It just has to fly 50 miles. It's not going to take longer because that USB stick contains more data. So, of course, for a sufficiently large file, the pigeon's going to win. So in BigO, the way we talk about this is we describe the pigeon transfer speed as O of 1, is constant time with respect to the size of the input. It doesn't take longer with more input. Again, with certain simplifications and assumptions about the pigeon's ability to carry a USB stick. But the internet transfer time is O of n. It scales linearly with respect to the amount of input. Twice the amount of data is going to take roughly twice as much time. So that's what BigO is. BigO is essentially an equation that describes how the runtime scales with respect to some input variables. So I'm going to talk about 4 specific rules, but first let me show you what this might look like in code.
And so one of the reasons that it's really nice to stop and learn BigO and relearn BigO if you knew it once and have forgotten or anything like that is when you are writing code at your day job, say there's a little function that you've got to do, it's a really great time and place to practice whether or not you are writing your code in the most efficient way that you can for the requirements that you have. And so it just, by having these tools at your disposal, you will hopefully be better programmers overall over time. So
let's consider this
but I can
function
speed
that
this
just
up a
walks
bit
through an
now.
array and checks if it contains a particular value. So you would describe this as O of n, where n is the size of the array. What about this method that walks through an array and prints all pairs of values in the array? Note that this will print, if it has the elements 5 and 2 in the array, it'll print both 2, 5 and 5, 2. So you would describe this probably as O of n squared, where n is the size of the array. You can see that because it has n elements in the array, so it has n squared pairs So the amount of time it's going to take you to run that function is going to increase with respect to n squared. Okay, so that's kind of the basics of BigO. Let's take another real world example. How would you describe the runtime to mow a square plot of land? So a square plot of grass. So you have this plot of grass and you need to mow all of it. What's the runtime of this? Well, it's kind of an interesting question, but you can describe it one of two ways. One way you describe it is O of A, where A is the amount of area in that plot of land. Remember that this is just an equation that expresses how the time increases, so you don't have to use n in your equation. You can use other variables, and often it makes sense to do that. So you can describe this as O of A, where A is the amount of area there. You could also describe this as O of S squared, where S is the amount of, is the length of one side. Because it is a square plot of land, so the amount of area is S squared. So it's important that you realize this O of A and this O of S squared are obviously saying essentially the same thing. Just like when you describe the area of a square, well, you could describe it as 25 or you could describe it as 5 squared, just because it has a square and doesn't make it bigger. So both are valid ways of describing the runtime. It just depends on what might be clear for that problem. So with that said, let me go on to 4 important rules to know with BigO. The first one is if you have 2 different steps in your algorithm, you add up those steps. So if you have a first step that takes O of A time and a second step that takes O of B, you can add up those runtimes and you get O of A plus B. So for example, you have this runtime that you have this algorithm that first walks through one array and then walks through the other way. It's going to be the amount of time it takes to walk through each of them. So you'll add up their runtimes. The second rule is that you drop constants. So let's look at these 2 different ways that you can print out the min and max element in your array. One finds a min element and then finds a max element. The other one finds a min and the max simultaneously. Now these are fundamentally doing the same thing. They're doing essentially the exact same operations, just doing them in slightly different orders. Both of these get described as O of n, where n is the size of the array. Now it's really tempting for people to sometimes see 2 different loops and describe this as O of 2n, and so it's important that you remember that you drop constants in BigO. You do not describe them as O of 2n or O of 3n, because you're just looking for how things scale roughly. Is it a linear relationship? Is it a quadratic relationship? So you always drop constants. The third rule is that if you have different inputs, you're usually going to use different variables to represent. So let's take this example, where we have 2 arrays, and we're walking through them to figure out the number of elements in common between the 2 arrays. Some people will mistakenly call this O of n squared, but that's not correct. When you just talk about runtime, if you describe things as O of n or O of n squared or O of n log n, n must have a meaning. It's not like things are inherently one or the other. So when you describe this O of n squared, it really doesn't make sense because it doesn't. What does that mean? N is not the size of the array if there's 2 different arrays. What you want to describe instead is O of A times B. Again, fundamentally, BigO is an equation that expresses how the runtime changes, how it scales. So you describe this as O of A times B. The fourth rule is that you drop non-dominant terms. So let's suppose you have this code here that walks through an array and prints out the biggest element, and then for some reason it goes and prints all pairs of values in the array. So that first step takes O of n time. The second step takes O of n squared time. So you could first get as a less simplified form, you could describe it as O of n plus n squared. But note that you compare this to O of n and the runtime, or compare this to the runtime O of n squared and the runtime O of n squared plus n squared. Both of those 2 runtimes reduce down to n squared. And what's interesting here is that O of n plus n squared should logically be between them. So this n squared thing kind of dominates this O of n thing, and so you drop that non-dominant term. It's the n squared that's really going to drive how the runtime changes. And if you want, you can look up a more academic explanation for when exactly.
So what she is saying right now is if you have something that is exponential, or n squared, it will be at a sufficiently large number. It will be so dominant in terms of the amount of time that it takes that it's really no longer relevant that the O of n is even part of the mix. It's like when you're buying a house, or when you're buying a car, or when you're buying something, or a new computer, or something really expensive, right? The cost of the entire house is, in Toronto, $1 million or $2 million, right? So when somebody says, oh, and there's $100 fee for changing the locks, you say, well, who gives a shit? So it's $2 million and $100? Like, who cares? And just like BigO, or you're buying a computer and it's $5,000, the video card is $2,000, and somebody says, would you like to spend another $5 to get LED lights on it that, that get fancy RGB lighting so you can have pretty colors? And you say, well, who cares? It's already $2,000. What's another $5? O of n squared is so dominant when that, so like, because if you look at 5 times 5 is 25, right? 10 times 10 is 100. So what's the difference between 10 times 10 versus 10 times 10 plus 10, right? Because O of n, if n is 10, you've got 10 plus 10 times 10. And so it would be, it's just at a sufficiently large number for n squared, n itself becomes irrelevant. And so and because big O notation is, there's algebra in it, there's math in it, but it isn't about the math or the algebra. It's about how slow is the function that I'm writing. And so when n squared is sufficient, or when n is sufficiently large, n squared is so much more dominant that you'd say, why am I even paying attention to this little shit? I don't care. I don't care about this little stuff. Let's just focus on the most important part. And so the most important, and that's why she's saying you also drop constants, because it doesn't matter. It's just, you're just trying to say how slow is my algorithm over time. And I think she might get to it. She might not. But the real way to tell is if you are looping inside a loop, you're probably in trouble when you loop inside a loop versus finding ways to just travel through a set of information a single time. So let's let her finish up.
But this is kind of a layman's explanation for it. We've now covered the very basic pieces of BigO. This is an incredibly important concept to master for your interviews. So don't be lazy here. Make sure you really, really understand this and try a whole bunch of exercises to solidify your understanding. Good luck.
Okay, there she is. She's done. And now I think I'll tell my story. I had an interview with Zynga earlier in the week at the beginning of last week, and it was a code interview, and they asked me an algorithm question, and I had to sit down and I had to solve it there was about a half hour to solve it. It was an easy question, and so it was not really about the solving the problem itself. And what I did was I just said, I sat down, I started talking about the question, and I said, I guess there are sort of multiple ways to solve this. I'm just going to start by trying to make sure I get something done that works. And in order to get something done that worked, I wrote an algorithm that was an n squared algorithm, right? So that means with a sufficiently large number, it's very slow. And I solved it, and it worked correctly, and we went through and did our testing, and everything was fine. And the interviewer at the end said, how would you go about improving the speed on this? Or how would you go about writing this in a better way if you did write it? And so I said, oh, well, I would use a Hashmap, and I would do all of this other stuff, and But because it was at the end of the interview where we finally got to the point where I was answering that question, the solution for how to solve it quickly was correct. I actually wound up googling the question as soon as I got out of the interview, and I said, "Oh yeah, so my first solution was the correct solution for the brute force method. The version that I said that I would do if I was in a different situation, if I was trying to write a faster version, was the correct version for how to solve it the correct way." But I didn't get a follow-up interview. And when I asked for feedback on why they didn't feel like moving forward on the interview process, the response I got was, for the years experience that I have as a programmer, they would have expected a better solution to come out of the interview process. And that's a really valid criticism in some ways, because one would expect the solution to be done the optimal way. There's a new message. Oh, feel that pain. Right. And so this is the reason that I think I wanted to make sure that it comes up in the homework later for the week, and in fact in this Nick White video as well, he talks about the way this works. So I might be a little too early in this, but the point is, number one, understand your BigO notation so that when you are in the interview, that's the interview process has been, well, honestly though, Rajat, it's part of the job to be good at this stuff. And so I think that it isn't necessarily unfair, because it's very well known everywhere we go. Like, let's take a second and look at, we had that one we looked at was the Amazon hiring interview guide. And right here, interviewing at Amazon.jobs. Like, the assessments. How do you prepare for the assessments? They say tips for software development engineers. It's like they tell you what they're looking for. They say right here, we are looking for your information on algorithms. We are looking for your understanding of distributed community. Like, they tell you everything that they're looking for before you go in. So it's, I don't know that I agree that it's unfair, because we also know what they pay on the other side of doing this stuff. So it's the reason that we study in advance of going to these interviews, is so that we are prepared to face these challenges when they come to us. They tell us what's coming. And if you think of, again, I think I said this in week 0 or week 1. If you are a lawyer, if you want to be a lawyer, you go to high school, university, then you go to law school, and then after 20 years in education, you go and you sit the bar exam, and if you pass the bar exam, they let you be a lawyer. If you want to be a doctor, you go to school for 30 years, and then you sit the medical practitioner's exam, and then they let you be a doctor. If you want to be a programmer at Amazon, you get paid at the same rate as if you were a doctor or a lawyer, but you've got to study for maybe 6 months to nail one of these interviews. And so, and that's a bit facetious. Obviously, people go to school for programming and stuff, but they tell you what's coming. You know what's going to happen. There are these sites that help you practice the exact types of questions that you are able to expect. And so I don't think it's unfair. I think it's just get better, get good, and then it won't be a problem. And that's a bit of a paradigm shift for me from my perspective on it, because I used to think that it was arbitrary and cruel to go in with these sorts of questions. What's this? Yeah, basically you just need to prepare for it, right? And what is that? Josh says, you are correct, that is unfair, but there is an expectation that you know how to do it and do it often, and it will be your natural solution to go too far. Right, so, Josh and I are in agreement there that this whole 14-week process is about preparing ourselves to, I've already got the job, so I'm cool. But but it is about staying on top of your game. I actually think that one of the things that I've learned in this time span as well is around actually keeping up with this at all times, because I think it does improve the quality of code you write in your day job. If you are writing the faster algorithm every single time, if you focus on making sure that every solution you write is an optimal solution, and if you practice your hacker rank maybe an hour a week, maybe 2 hours a week, and you just keep doing it for the course of your career, then none of this is going to feel like a gotcha when you actually show up on deck to try and write these things. The trick is to get this stuff so it's a little like playing the piano, right? You've got all of these chords, and in fact, I think one of these things. I thought I wrote this down, but it's like. We'll talk about that later. Or now. We'll talk about it now. So there's only a handful of question archetypes that come up in these interview questions, right? You've got arrays, stacks, queues, linked lists, trees, graphs, hash tables, heaps, sorting and searching. If you listen to Gail Lackman McDowell, she'll say, listen, dummy, it's always a hash map, right? So it's like there's only a handful of solutions. Call them 50 solutions for 1,000 problems. Like if you go to LeetCode, I think there are 1,800 problems. LeetCode, right? So you go to the problem set for LeetCode, and there are. Let me sort by number descending. Can I do that? No. There you go. There are 1851 questions on LeetCode. And there are probably 50 algorithms, right? And so every single one of the questions that you're going to run into, and we sort by difficulty, like, so you go through, you solve the easy ones, and then the medium ones. And if you think of the easy ones as piano chords, right? So you go dun 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 dun, and every algorithm solution is a different chord. So it's like use a hash map to do this, dung, or use a or they're building blocks and like Lego. And so the easy ones are your basic chords, whereas your medium ones might use two different solutions together, two different patterns. And then the hard ones maybe use 5 patterns. But at the end of the day, each of these solutions that you're going to go through has to answer the same questions. How do I turn this question of how do I go through this array of information? How do I go through this set of data? And how do I go through it instead of looping through it twice? Is there a way to loop through it once? Instead of searching one after another, is there a way I can first sort the array and then so I sort it and then I do the solution in n log n time, because in a sorted solution you can do things a lot faster. And so the idea of, again, like using your algorithms as piano chords to solve the problems will mean, but just like when you're learning to play piano, you've got to practice the piano. So you've got to practice this is doing your scales, right? Do 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 do, or playing chopsticks. Do 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 do. These are your algorithms, are your chords, and if you want to get to the doctor and lawyer level salaries, you want to be able to play your chords, right? Or even if you just want a one step, if you want to go from junior new in career developer to an intermediate developer, you want to be better at your chords than you used to be. And so this is about practicing. And so my realization is that this is not arbitrary, but if I was a musician who never played, who never practiced, then of course I wouldn't be as good as a musician who practiced, right? So that's, I think, it was a bit of a revolutionary way of looking at it from my perspective, and I think it's really valuable. This guy was really good. The one thing he said that was important here, BigO was how your code slows as your data grows. And that was, I think that's a really good rhyme for figuring out what it is. It's a really good mimetic device. I would suggest watching this 30-minute one because it was really good. We're going to move on to Gail. Again, she's going to say, this is the one where she says everything's a hash table.
Hi, I'm Gail McDowell, author of Back in the Pudding Interview. Today's topic is one that you really don't want to miss: hash tables. A hash table is possibly the most useful data structure for interview questions. Comes up all the time, both in interviews and in real life. In fact, one technique I often tell people is just, for any problem, have hash tables at the top of your mind as a possible technique to solve the problem. So let's talk a bit about what a hash table is. At a high level, a hash table is a key value lookup. So it gives you a way of, given a key, associating a value with it for very, very quick lookups. So suppose you had some situation where you needed to associate somebody's name with some set of information. A hash table would be the perfect solution for this problem because you can just put this into the hash table and then you can say, okay, give me the data associated with Mary, and then boom, we can get that information immediately. So in a hash table, the key as well as the value can be basically any kind of data structure. A string is often used, but it could be a circle, a square, a person, pretty much anything as long as you have a hash function. So what does that mean? Well, let's turn to the implementation to talk about that. So at a high level, we do want to store the objects in an array. So let's picture that. But how do we actually jump from a string to a particular index in the array? Well, that's what a hash function does. So So a hash function takes in a string, converts it to some sort of integer, and then remaps that integer into an index into that array. And then that's where we can find the person we're looking for. So it's important to understand that the hash code is not actually the index in this array. We map actually from the key to the hash code and then over to the index. And one of the reasons for this is that the array that actually stores the data from the hash table might be much, much smaller than all the available potential hash codes. And so we don't want to have an array of 3 billion just because there's 3 billion potential hash codes. So we actually remap it into something smaller. Now, note here that two different strings could actually have the same hash code. And that's because there are an infinite number of strings out there, but a finite number of hash codes. So it's theoretically possible for Alex and Sarah to actually have the same hash code. Additionally, since we're remapping the hash code into an even smaller index, two things with different hash codes could actually wind up mapped to the same index. So what do we do with this when this happens, which is called a collision? There are different ways of resolving collisions, and I really do encourage you to look this up on your own time, but I'll just talk about one of them, which is called chaining. And chaining is possibly the most common one, and it's very simple. What it basically means is just, hey, when there's collisions, just store them in a linked list. So rather than this being an array of people, it's actually going to be an array of a linked list of people. And so that means, though, that when you get a call to say, hey, get the value of Alex, you actually need to look through all the values in that linked list and pull out the value for Alex. Now, as you'll note here, this linked list contains not just the actual person objects, but the actual original keys as well. And the reason for that is that if you only store the person object, you'd see all these people who map to this index, but you wouldn't know which one they are. And so you actually need to store the keys with them. So when you get a call to say, get me the value for Alex, then you actually call this hash function, you get a hash code back, you map over to this index, and then you walk through and look for the thing with the key of Alex. So that's the basics of how a hash table operates. So let's walk through this from start to end. We're going to have this hash table class that underneath it has an array that actually holds the data. And the array isn't going to be an array of the actual values, it's going to be an array of the linked list of the values. Then, when someone says, put the value of Alex, put the value of Alex mapping to this person, we call this hash code function that gets us back the hash code. Then we map from this hash code over to an index, and that gets us over to this index in the array, and then we put it into this linked list. If there's nothing else, great, then we're just going to have it in one element linked list, but there can be multiple values in there, in which case we walk through it. Now, what if there were already a value of Alex in there? Well, then we just fix that value immediately. So let's talk now about the runtime of a hash table. Well, it really depends on what we're talking about and what assumptions we make. In many cases, we assume that we have a good hash table and a good hash function that really distributes our values well. And so for the purpose of an interview, we often just summarize this and say, okay, getting and setting in a hash table is constant time. In reality, if something weird happens, we have a bad hash function, blah, 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 we could also say it is linear time in the very worst case. But for the purpose of most problems, we generally talk about constant time because in the real world, we're going to make pretty sure, hopefully, that we have a good hash table. So this is a bit of a high-level view of what a hash table is and how it works. There's a whole lot of complexity you can dive into here about different ways of handling collisions and exactly what happens when a hash table...
So these are useful to know. I think in terms of the interview, it depends on the scale of the place that you're going to. I mean, I would expect something like this might come up at an Amazon, but at a mid-level or intermediate or lower level position, you probably wouldn't see that. But anyways, that's...
Table, you start to put a ton of elements in the hash table. How does it grow with new elements? Can be resized? All that sort of stuff. I really do encourage you to go look at this stuff on your own time. It's a fantastic thing to really understand a lot of the complexity here. But for the purpose of a lot of interview questions, we just sort of simplified all this down and summarized things as, let's assume we have a good hash table, and so we get this beautiful constant time insert, find, and delete. So now that you understand the basics, go ahead and do try to learn these more complex details of hash tables, but also go practice some of these basics on your own time, on your own problems. Good luck.
All right, so that's Gail's position on hash tables, and again, like a bit more detail on that. I think probably I could have picked off one or two more of these, so I think I kind of also already covered what I wanted to get out of Nick's video. You're welcome to watch it on your own, but the practice, here we go. So the strategy for getting better at these algorithms is to practice, again, the piano analogy. So let's look at, like, this one has a solution. So let's look at two of these. So start with this one. running the sum of a one-dimensional array. Given an array of numbers, we define a running sum as nums 0 to nums I. Return the running sum. So with an input of 1, 2, 3, 4, you should have 1, 3, 6, 10, which is 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, and that's a running sum. So one of the suggestions that I've read that I like best in terms of how do we do this, this one would be pretty easy to solve, so it's not really that big a deal. But what you should do is set a timer. Okay? I said set a timer for 30 minutes. You can do whatever time is reasonable from your perspective. But you set a timer and you start trying to solve the question. I close this. So you try and solve the question, and as soon as the timer goes off, whether or not you have the solution, you can either go to, whether or not you have managed to solve it, you can jump across to a solution if they have one. And so this has a pretty in-depth write-up. It includes code in various languages. If you are writing, for example, in JavaScript and they don't have one, then you're going to have to use a bit of heuristics to kind of say, oh, well, maybe Java's a little easier to read. And you say, okay, so they're doing they're doing a loop where they create a new array, so that, they're creating a new array, they loop through each of the elements, and they return the result. And if you go through the thing that you can see by reading this solution is you get detailed information. In the previous approach, we created an extra array to store our results. However, we don't actually need to do so. We can obtain the same result without using extra space by doing the work in place. And so what you get by reading these ones that have proper, full, robust solutions is you get that level of analysis where you understand, you say, oh, this is O of n. This is O of 1 in terms of space complexity. Whereas this one here is, if you solve it this way, well, that's the same answer, isn't it? You jerks. It would be nice if the example that I happened to pick had, different version, because sometimes they'll have, oh, this version of the problem you solve in O of n squared, and then this version of the problem you solve in O of n. And the really nice thing about that is it gives you a better sense. You can look at the pattern used in this one, then you scroll up, you look at the pattern used in the one above, and that's all really helpful in helping you understand and work better with these problems. Now, the reason I say set the timer, don't bother trying to fully solve any of these things. Much like, again, learning a musical instrument, actually, this is unlike learning a musical instrument. This is not a case where perfect practice matters. There's a theory in in learning where we learn more or we retain more of the things that we work for. So by putting effort into trying to solve it, we set ourselves up to be in a place where we are receptive to to retain the knowledge that we gather. You can go through and you could solve it yourself entirely. Probably for the simple ones in a half an hour, that's great. You probably will. But there is a point where after 30 minutes of trying to solve it, you probably know enough about what you don't know that when you see the solution, you will have that aha moment anyways. And then because there are 1,800 problems to get through, you can try again on the next problem and hopefully solve the next one in 30 minutes. The value of having that 30-minute time window. Oh, somebody else is here. Somebody's new. SOC analysis is not a... Sorry, I have to read the chat here. Detox Mango is not... And security engineers have more compensation than software engineers on average. I do not have an answer to that. And so if you have any information on that, that would be interesting. But I don't know. SOC analyst, SOC analyst is not a security engineer. I don't know. Sorry. So yeah, yes. So the if you work a little bit at trying to solve it, you come along and you read the solution, you will be better able to process, oh, that's the thing that I was trying to solve, and you can use that on the next problem that you come along with. So for some of the problems in LeetCode, you will have solutions available to you. So here's the list here. You will have solutions, doobie, right? These ones have the solutions. If they don't have solutions, you can just hop over to the discussion, and you can, here's a simple JavaScript one-liner solution to the IP address thing, right? So in here you go. So this is so the value that you get out of trying it first is you sort of prime yourself to be ready to fully understand what's going to happen, and then you go ahead and move on to another one. The 30-minute time window is an attempt to put you in a mode where you are prepared to solve the problems in the time window that is typically allocated to a problem within a... Have you taken a look at a hedge fund or co-locating project? I'm not sure. We're really talking about trying to prepare for code interviews, so I'm not sure what your a hedge fund co-locating project. Not sure. But I've definitely just forgotten what I was in the middle of saying again. So that's okay. Right. So we were. Oh, yeah. So you want to set yourself up so you are preparing. You are. You set yourself up so you are prepared to answer questions within the 30-minute time window that is typically allocated to a tech interview. And so that's why you should set the timer, solve without assistance for 30 minutes. If you don't get it in the time, look at some solutions, make sure that you finish solving. And one of the other things that happens, especially I've found this more often on Hacker Rank than I have found it on Leet Code, is some of these problems that you will come across on. Wait, no, where are my actual tests? Show me actual algorithms questions. So you go into there. Never mind. Each of these problems that you go to solve. What was this one? I did the hardest one. So this one, for example, if I look at the submissions that I've done here, so they actually have 50 test cases, right? And so sometimes you can have a solution. For example, I had a solution here where I passed 49 of the 51 tests, and then it says, but your test doesn't pass when you are when you have this input. And so you go, oh, I wrote all of this code. Was this my code? That's a huge amount of code for this. This was also considered one of the hard ones. But you say, oh, I can't solve for this, and then you have to rethink to how do I solve for these individual test cases, and so there's value in stopping and getting a hint, or going over to the solution page, or going over to the discussion forum, and working through it. I think 8:20 is a good time. So let's look at our learning objectives. First of all, what topics are going to arise during a code interview? These ones. Okay. Second, where do we find resources on the expected topics? Well, I didn't do a great job of that, did I? I have Trend Black. I have Gail's work. I've got to do better for next week at getting more resources around these other topics. I guess if we look at these 2 pages, are they free though, or are they 182 lessons? I expect that these are paid. I want to find us free. Yeah, I want to find us free resources, and so I'm going to do a better job on that. That's a to-do for me. So be aware of where to find tech resources on the expected topics. Understanding BigO notation, I think we probably have a good sense of. We watched 2 videos on it and talked about it extensively. Being able to estimate BigO, we haven't talked about that in detail, but I think it was Jeff Wong, actually. Jeff, who tried to tell me how to pay attention to BigO, and he says basically you just count the loops that you have. If you loop through something within another loop, you're probably n squared, and you just get a sense for scaling over time. But that's one of the things you should do when you are writing code from now forward. Try and keep in mind that you want to think about the BigO. Trying to here. Let me see. Mississippi Dog, you are new as well. Thank you so much for coming to join. I'm trying to figure out if I'm going to use Java or Python. I know Java has a steeper learning curve, but I'll understand it more. Python doesn't dive deep into the things under the hood. Now, Mississippi Dog, who are you targeting? Do you have a specific company that you are trying to get to? And do you have any languages that you already know? Because these are some of the things we talked about this in week 0, actually, and there are a lot of factors that go into selecting your language, but we could kind of work together to come up with a best solution for you. I gotta scroll down to see your income. Count how many times you go through your entire set of data, not the loops. You can loop and break early, which wouldn't be O of n. You can loop over everything more than once, or your data can change in the loop. What matters is how many times your code runs versus the number of values in your data. Yes, but if you loop through, and this is the way that Jeff presented it to me, and so it's a really good discussion topic to have because I need to know this better too. And my understanding was, if you loop through something once, let me bring up something, and so I go up here, and hopefully Mississippi Dog is still typing, so we get to talk about that a little more too. But so I've got 2 functions, right? I've got function. Let me change this to JavaScript. So I go JavaScript function foo, and I've got var n equals an array. So if I go for let I equal 0, I is less than n dot length I plus plus. So, I say loop once, and then I do this again, loop twice. Well, this actually turns into the O of 2n, because I go through on a linear basis once, I go through on a linear basis twice. Now, if I take this same package and I do it like this, and this is now j, dupe j. Well, this is loop once for every element in n at I, right? And so that one becomes O of n times n, which is n squared. Whereas this one, because we drop constants, which is O of n. Now there are more comments that have arrived since then. BigO looks worse, so it's the worst case. Yeah, and also the BigO notation is about how does your program slow as your data grow. So that's the And this has taken me I mean, Jeff has been gone from our daily working life for years, and I was asking him how to do this while we were working together. And so this is definitely something that's still like you've always got to think, you've always got to keep working on it and keep thinking about it and trying to figure it out. So anything from Mississippi Dog yet? I don't have an answer without more context. And I won't have an answer anyways. It's just about opinions. Oh, here, yay! Let I equals less than. It's also a loop, but I don't know that counts if you're not doing it. Yeah. So Mississippi Dog says, I know Python, but companies are using it pretty much for automation, machine learning, or AI. Yeah, and those are really, really high paying fields. And so if you want to work on large scale applications, I don't know that Python is considered slower than anything else. Especially when we start talking about BigO, because it's about the algorithms that you're writing, not necessarily the underlying language itself. I'm trying to get into any of the FAANG companies. And so I really like Facebook, Amazon. Amazon loves Java. Currently is software engineer 2 in the defense industry, trying to get into that big tech world. 100% point B. So for Mississippi Dog, pay attention to the codinginterview.com website. First of all, that is linked up in the, I will actually paste the tech interview prep course URL. This is where all of the channel notes are for you. So you can go here. The week 0 content is where we kind of talk about... Oh, try reloading. Something's wrong with my chat. Okay, is there more? No, that's... Here we go. So... This guy, here we go. So let's go back up to the interview guides by company, specifically Mississippi Dog. You said you liked Amazon, you liked Facebook, but you would take anybody. So let's look at a few others. So Amazon, for example, if we click read about the process, you can actually see, so Java, Python, Ruby. What is this Onion? What's the Onion language? Right, so if you want Amazon, both Java and Python are good languages to choose. If you want Facebook, both Java and... Is this still Facebook? Is this right? There you go. Why don't I see PHP in there? I would expect to see PHP in there. Java and Python are both good languages to choose. Yeah. Onion is Perl? Did we know that last time? So Netflix, you read about the process. You go, well, what do they use? So if you wanted Netflix, Java, C#, C+, JavaScript is huge at... And what is this? Open image in new tab. Does this have the... I don't know what that stripy, spinny one is. Swift, that makes sense. Let's look that up. Swift language logo. Nope. Not Swift. Anyways, and also, I shouldn't be Googling live on Twitch or I'm going to get banned when like boobs show up or something. So I've got to remember to Google things off screen unless I know that they're on safe websites. Now, here you go. Once again, Google wants Java, wants Python, and Golang and C Sharp. So all of that said, so step one, Python is absolutely a perfectly acceptable choice because every single FAANG or big tech that you're going to be looking at is going to want people who know Python. The other thing to think about, though, is especially if we are looking at Amazon, then Amazon has a really serious section of their interview process dedicated to object-oriented design. You would likely have a question in your is it Pearl is the onion? Or is Pearl the spinny thing? I don't know what the spinny thing is. But Pearl sounds right. I'm going to... Well, somebody else can find it. But back to Pearl is the onion. Scala is the red spinny thing. There we go. So in your Amazon interview, expect a question like design an object-oriented or design the objects for a car, or design the objects for a, I don't know, something. You know, they ask questions about designing the objects and the inheritance and the design the objects for animals, right? And so like design objects for dogs. So if you're looking at Amazon specifically, you want to be good at your object-oriented design, and if you are using Python in your designs, you are not necessarily guaranteed to be, you know, I think that the Python designs that I have seen are not heavily object oriented. They're more sort of scripting or I wouldn't just they're structured programming, but they're not necessarily object programming, even though object-oriented programming is supported by Python. So Java is probably, if you are targeting big tech, Java is a good one to learn as long as you are interested in learning it. Also, I'm gonna Google this off screen. I think it's called Kotlin, Kotlin. Kotlin programming language is a Kotlin is also effectively Java, to my understanding, or it runs and builds directly out to Android natively, and I think my understanding of this, I'm not perfect on that. My understanding is, most resources. So if you could use Python, you should. Yes. Are there good resources for learning data structures and algorithms for Python? So yeah, I would say that some of the things that we've been going through, first of all, let's go back to the LeetCode or HackerRank problem-solving systems. You know, here, fancy sequence. I can just click on one of the ones that I haven't done before. You can go right down here. Bam. Now you're learning algorithms in Python, right? Don't start on the hardest ones. go to the. I think I don't know when you joined, but one of the strategies I think that we should consider using is start on the easy problems, because each of the types of solutions that come up within the easy problems are the building blocks of the solutions that go into the medium problems. And the medium problems are the building blocks that go together to make the hard problems. And so if you can get to the point where you can solve the medium one, the easy ones, snap, 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 just like it's second nature to you, like the first solution that comes to mind is the optimal solution for an easy one. Then you move up to the medium ones, and then you go snap, 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 and you're solving it out of these building blocks. So shuffle the array, right? You go in, you say Python, given the array of nums consisting of 2n elements in the form blah blah blah, return the array blah 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 blah. And so you learn the algorithms by doing the problems. In terms of the data structures, it's pretty similar. I would go so far as to say if you go to HackerRank, it's really nicely divided into sections. So you've got an algorithm section within HackerRank. So if you want to learn algorithms, you start at the top of this list and you just keep going until, and this one's nicely structured because this one is built, it says easy, 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 and eventually they start throwing in the mediums, and you can just go through and you can learn your algorithms by going through this structured HackerRank thing. And you want to learn your data structures, start at the first one. So if I click on this, I've got to log in. So I'm going to move this off screen so I can log in. I believe, is this me? It might remember who I am. I've probably done some. I've done some of these on one of the courses. So here you go. So you want to learn Python. There you go. You have your choice. You have Python 3 or Python 2. So you go in, you've got yourself dark mode. Fancy. That's not as dark mode as I expected. Right, but this is a data structure question to do with arrays. And so you learn by practicing. If you want to learn on a different level, like you want to learn in terms of here are some of the other resources that you can look at that I've actually pulled together myself. So cracking the coding interview is a really great resource. It's got much like HackerRank, it has the problems in it, but it also has short introductory chapters to each of the things that you might come across. One of the other things I just picked up a couple of other books. I'm starting to work my way through Clean Architecture, which is, this one is more about how to design large software systems for long-term maintainability and reducing the cost of changing it. This is more a senior developer's book that I would not recommend. If you are still learning algorithms and data structures, this is a next step. But one of my plans, I said this on Twitter just the other day, was I've made it a few chapters in, and I'm going to be summarizing these in short videos as I read it. So I think this weekend I will be doing my first short video on this. And so you might not even have to read. Yes, and Clean Code I have on order, and it's on its way. And here is the last one that I've picked up just recently, and it is Design Patterns, Elements of Reusable Object-Oriented Software. This one, if you are interested in learning about object-oriented design, is actually going to be useful. This is one that you would probably have value in, but you do not have to buy $100 book to. Actually, I think I got that for $50 on Amazon in hardcover, so that's pretty good. But you do not have to buy the entire Design Patterns book, because if you go to Wikipedia and you search for Design Patterns, you actually have a really great guide. Let me see. Right, so each of the sections in the Design Patterns book has itself a proper write-up in Wikipedia. So, and it comes with examples. So you have a Python example for what is this? This is a chain of responsibility, and so it gives you a summary of the pattern by name, and you can use that to, let me see. I prefer Head First Design Patterns, makes it easier. Yeah, so Head First Design is one of the other ones that I saw when I was searching. Head First Design Patterns. And it had a really cute cover that made me think it was fun. So here, Head First Design Patterns is supposed to be, and the brain-friendly guide. There was something, I think at one of the points I looked at, there's, on some of these you can actually look inside the pages, and it sort of said, oh, we wrote this one to be a very fun and human readable book on design patterns, and maybe I picked the wrong one, but we'll see. We'll see. I'm just trying to work my way through these things. But anyways, okay. So in terms of this week's homework, I thought I added this in. So readme, save. I thought I pushed that. Oh, maybe I'd have to push it again. Do this. There we go. Okay, so week 2 is in place. In terms of homework, again, entirely optional because this is a self-study course, but there are no grades, except there is a chance at having a wonderful new job at the end of it if you practice and get good. So, I thought it would be a good idea to solve 4 easy ones using the 30-minute time window block and a massive exam. Yes, a massive exam with a massive payout in theory. So solve 4 easy, 1 medium algorithm problem. Set yourself the timer for 30 minutes apiece. I don't think for the easy ones that you're necessarily going to need the whole 30 minutes, and you're probably not going to need the solutions page. You might need it for the medium one. That's fine. Over time, with continued and scheduled practice, these get easier, like playing the piano. Dun, 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 dun. Dun, 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 dun. Anyways, so that's the story. That's the week. With 10 minutes to spare. Ta-da! How you feeling, Mississippi Dog? Thank you for coming. You feeling better? Feeling confident in your choice to learn? I'm really happy. I'm really happy there are other people showing up. This was really exciting. Do we have anything else we want to talk about before the sign off? How did we do? How do we feel about this week? The GitHub, yes, I will drop it in chat one more time. Tech interview prep course. Oh, you know what? Here you go. Let me see if that one comes through. There it is. It came through this time. Yeah, my stream broke the last time. Actually, Rajat, I'm also looking forward to doing these. I think this is the part. These get fun when you start doing them like this. And Josh, the referral program is such that I have a non-solicitation clause in our contract, so I cannot actually ask people to apply to my new employer, but if they applied on their own, I would happily give recommendations. I don't know that there's a referral program, but I wouldn't. My number one. Okay, so you see what I'm saying. That's very clear. But my number one priority is not really about. I wouldn't go about helping friends just for a referral. I'd do that for free, and the referral bonus is a bonus. So that's definitely I helping people is its own reward. And so if you would like to discuss that, we can absolutely discuss that. And in fact, as I told you off the top of the lesson, a portion of my new role is to assist with recruitment. And so if suddenly on day one of my new job there were 5 really highly motivated, highly qualified candidates saying we want to come along, then it would probably look okay either way, right? So I would not be upset if you decided to apply and use me as a reference. So, but I am not soliciting you. To be very clear, I'm not, because I already know that you're looking, and it doesn't. Anyways, yeah. So, but yeah, yeah. So that's it. That's the week. And next week is actually more of this stuff, but you are not. That's true. You did. You asked first. So next week is going to be more of this stuff. I'm going to try and figure out which of these really need to be dug in. Like tries, I actually have no idea what they are. Sorting and searching, I think, are both things that they spend a lot of time on in first year computer science, and heaps seem like they're important. So I think next week I'm going to try and do these heaps, sorting, searching, and tries, because those are the ones that I think are hardest. And we'll maybe follow up and talk about algorithms and stuff. See if anybody had some that they particularly enjoyed. Maybe we will share each other's scores on HackerRank. How have we improved? This is funny. If I log in with the right account, I have like a lot of points in HackerRank. Let me see. So I'm logged in. 313 more points to get a badge. I thought I had more points than that. I'm a silver. I wanted to be a gold in problem solving. So that's one of the fun things about Hacker Rank, though, is like you get little badges and you can start competing with each other. And like, I think the whole platform is intended to be paid for by. Actually, this is probably of value to you, Mississippi Dog. Is the question on this stuff is follow the money, right? Like, so we've got this incredible website here, Hacker Rank, where you can just sit around and play these coding problems all you want. Doop, doop, doop. I'm having fun. I'm doing machine learning. I'm doing Python and whatever. But who's paying for this website to run? Well, FAANG companies are paying for this website because they pay to list their jobs on the site. But more than that, they pay for the data to query directly the list of people who do very well on the problems. So, playing practice on Hacker Rank, or I assume LeetCode, or I assume any of these other guys, is not just about getting better. It's about raising your profile to the people who are hiring. So let's look at it. Let's go location. I don't know if they'll have a Toronto in here. Can I type Toronto? No Toronto, but let's look in Seattle. So there might be some. So Foursquare. Is Foursquare even still a thing? California Bay Area. Well, let me tell you that this used to be a lot more impressive because the jobs that were listed were all like, they were all like Facebook and stuff. It was, so maybe Hacker Rank has fallen out of favor there. But anyway, the point being is people are buying the data, and they will start reaching out to you as your score improves on these things. And so if you are looking for your big tech job, if you are looking for your FAANG job, you by just doing this. Who's another one that's really good? I'm gonna have to search off screen because I can't remember their name and I don't want to be I will remember at some point who this other one was. But there are definitely some of these coding problem sites that are specifically geared to finding the best candidates, and they sell that information to the hiring companies, the companies that are hiring, and they will approach you. And what that means is you're able to get to the front of the line in terms of getting through to your interview. And so this running these algorithms, it's more than just practice, it's profile. And so, and by next week I will have that one that was really good, because they had their questions were so hard. Crap, I wish I could remember. I'm upset now with myself because I'm having a total mental break. Anyways, there we go. That's the week. It's 9:00. Thank you all for coming, and I will be signing off, and we will see you hopefully next week. And feel free, you can actually reach out to me directly at any time as well. My email is not here, but it is, where is it? You can find me. Where can you find me? I will have to add my, yeah, thank you. I'll make sure my contact info is on the repo so that you can start reaching out to me directly. You can comment on YouTube. You can submit an issue on the tech interview prep course. So, actually, there you go. If you have questions, you can actually just reach out to me in an issue, and I will make sure that I get some contact info there for people to get me other ways. And we will see you next week. Yay! Thank you so much for coming.